Hello everyone! In this lesson, we will continue to study the frequency domain analysis module of continuous system. In last lesson, we reviewed the main properties of Fourier transform and explained their physical meaning. Today, we are going to discuss the engineering application of frequency shift. We mainly analyze amplitude modulation in time domain and spectrum shifting in frequency domain. We have learned two important formulas about spectrum shifting. First, if the Fourier transform of ft is fj omega, then ft times cosine omega 0t can be expressed by formula 1, and ft times sine omega 0t can be expressed by formula 2. For formula 1 and formula 2, when ft is multiplied by a sinusoidal oscillation signal with equal amplitude, the spectrum of ft is shifted by omega 0 units, and it is shifted to the left and the right, respectively. We have also discussed the frequency spectrum of cosine omega 0t, because in the actual signal analysis, it's more convenient to analyze the cosine function, so we use spectral characteristics of cosine omega 0t, as shown in formula 3. We can find that in the frequency spectrum of cosine omega 0t, two impulse functions with intensity pi are generated at omega 0 and minus omega 0. Let's look at a simple AM wave, rectangular AM signal. It is known that the rectangular AM signal ft is equal to big GT times cosine omega 0t. Here, GT is its rectangular pulse. Its amplitude is E. Its pulse width is tau. Find the spectrum function of this AM signal. This is its time domain waveform. We have learned the frequency spectrum of the rectangular pulse signal changes according to the law of the sampled signal. In other words, its frequency spectrum is E tau times SA omega tau over t. According to the expression of the AM wave, and according to the Euler formula, cosine omega 0t is expressed by an exponential signal. So formula 4 is true. According to the frequency shift, for the signal of AM wave, a spectral density function should express by formula 5. Let's take a look at its spectrum. The frequency spectrum of the rectangular pulse changes according to the law of sampled signal. If the rectangular pulse is multiplied by cosine omega 0t, we can get a spectrum as shown in figure 2. Here we can find that the spectrum of the original rectangular pulse is shifted by omega 0 units to the left and the right, respectively. Of course, the rectangular AM signal is a special AM signal. It did not change the amplitude of the original sine wave. It just intercepted a section of the sine wave. That is to say, it has a truncating effect on the sine wave. This truncation certainly has a corresponding effect on its spectrum. Its spectrum is more discrete than the original. Let's look at an actual amplitude modulation signal. This is a modulator. Its input is xt and yt. Xt is a low frequency signal. It is called a modulated signal. Yt is a high frequency oscillation signal. After xt is multiplied by yt, that is to say, after xt and yt enter such a modulator, its output becomes xt times cosine 2 pi f0t. Let's look at its time domain waveform. As the original constant amplitude oscillation is modulated, its amplitude changes according to the law of the modulated signal. This is commonly known as AM modulation. Let's look at the spectra. This is the spectra of the cosine signal. The two impulse functions are generated at f0 and minus f0. Suppose that the spectrum of the modulated signal changes according to this law. For output signal xm, generated from the modulator, a spectrum is formed as the spectrum of the modulated signal is shifted to f0 and minus f0. That is to say, spectrum shifting is generated. Amplitude modulation is a widely used analog modulation method. The modulation in which the amplitude of the sine wave changes with the modulation signal is called sinusoidal amplitude modulation. Here, AM refers to full amplitude modulation. The time domain and frequency domain characteristics of amplitude modulated waves can be simulated by software emulation. For example, Figure 4 shows the output waveform of an oscilloscope in an AM modulation simulation system. This is a modulated wave. This is a modulated signal. Obviously, the envelope of the modulated wave changes according to the law of the modulated signal. In engineering, there is another concept called demodulation. Demodulation refers to a process in which the original modulated signal is recovered from the modulated signal. Let's look at Figure 5. Figure 5 shows the spectrum of a modulated signal. In AM signal, the carrier component does not carry information, but it has most of power. If the transmission of carrier components is suppressed, power efficiency can be improved. Then we call this technique double sideband modulation that suppresses the carrier. Of course, single sideband modulation is an amplitude modulation technique that can achieve more efficient usage of power and bandwidth. It is called SSB. So, in addition to AM modulation, there are many other amplitude modulations, including DSB and SSB. Let's look at a waveform simulated by MATLAB. This is the waveform of a modulated signal. This is the waveform of a high-frequency carrier. This is the waveform of a modulated wave signal. And this is the waveform of a demodulated signal. Figure 7 shows spectrum waveforms generated by simulation software. This is the waveform of a modulated signal. Obviously, here you can find that the modulated signal does not have single frequency. It has two frequencies, which is called dual-tone modulation. This is the spectrum of a carrier. This is the spectrum of a modulated wave signal. And this is the spectrum of a demodulated signal. We will discuss the detailed content of amplitude modulation in the communication electronic circuit. Today, based on frequency shift of Fourier transform, we studied amplitude modulation and spectrum shifting. So much for today. Thanks for your listening. Goodbye.